Анастасия, скажите, пожалуйста, вы видите мои слайды?
Да, все хорошо видно.
Хорошо, тогда я сделаю сейчас полный экран, и мы начнем. Ну,
Да.
как вы считаете, можно начинать? Что?
Я думаю, да. Окно Тимса тоже видно будет.
Будет
То
видно,
есть
да?
мы
Сейчас
видим
я...
абсолютно все, что видите вы на своем экране.
Потому что раньше всегда было так, что вот есть маленькое окошко, потом оно тоже исчезает, и я вижу только свои слайды, и никого, ничего больше не вижу, из Тимса ничего не вижу. Но я не знаю, как получится, посмотрим.
Его можно свернуть, вот на такой минусик нажать. Ну,
Нет,
можно оставить
наоборот,
просто.
мне хочется кого-то
Ладно.
видеть из публики. В частности, если я вас вижу, то мне очень приятно. И, по крайней мере, я вижу хоть одного слушателя. Это помогает делать доклад, чем просто говорить в компьютер, если никого не видишь. Ну, ладно, посмотрим. Так или иначе, я думаю, мы можем начинать. Well, dear listeners, we start our seminars in this new academic year, and our first seminar, I will present our recent result about mathematical modeling of EEG data. EEG is electroencephalography, and I will first of all briefly recall about that. Of course, all that is very well known, and this I took from my some old presentation, and in fact, it's some information from Wikipedia. And in fact, EEG, so it starts, you see this a part of this article from Wikipedia. It's a long story. It starts already in the 19th century, but mostly what was very well known already in 1920s, and also you see this photograph here. This works by Hans Berger, who discovered what was called during quite many years Berger waves or Berger rhythms. Now it is not so often called like that. It is because all these signals are often represented according to the frequency range, frequency band, and this Berger rhythm, they correspond now to alpha. They call, rather often they are called now alpha. It's about 10 hertz. Some range, it's not exactly, it can be from 6 to 10, from 8 to 12, some range of frequencies around 10 hertz, and physiologically they're quite important. Of course, during these 100 years, there were many studies, many results about this EEG data, and it's a very active area of research. Like curiosity, I also took here from Wikipedia. You see this in the right part. Well, I will try to maybe to. Yes, to open this pointer. Yes, it's kind of curiosity. I don't know how whether the studies are continued or not, but I was very much impressed when I read about that they took several people and they connected them by these EEG electrodes, and they suggested these people to somehow synchronize to guess their answers, and it appears that the result was amazing. The result of success rate was about 80%. So it looks like two people connected by this EEG electrodes can guess what another one thinks, right? Well, truly speaking, well, it sounds amazing. I don't know how true is that and whether the studies are continued, but this was written in Wikipedia. Well, another very active area of research is, of course, brain-computer interface, and it's also a huge and very important area. And a couple of days ago, maybe even yesterday, I have read that Elon Musk looks for volunteers to introduce electronic chips in the brain. So it's kind of amazing. Because, well, I have heard and read something about that long time ago, and in particular that he got a permission from all these public health authorities. It's not at all obvious. For example, I'm sure that in France it's just absolutely impossible. It would be absolutely impossible to get a permission like that. But they got it, and they're looking for volunteers. So I think all that it's very exciting, and make me think about these science fiction movies like Terminator and the others, when we have all these robots going around. So this is our future. Okay, but I will not discuss, of course, this today. It's kind of science fiction for me. I will discuss some of our recent works we did, like basically last year and this year. So to very briefly recall how all that represents. So we see here this young man with this EEG electrodes, this cask. Usually it represents like a cask with some number of electrodes. The number varies from several to the maximal, I think it's 256 maybe. They are located on the scalp in some particular way, and they have their names, as for example shown here, with all these letters and numbers. And this helps to have some kind to have a kind of unification of all this data and this text. But I should say that I'm not, of course, specialist in EEG, because it's a very particular area which requires various particular expertise and also data treatment. Here I give just an example, because I collaborated with a startup called Team, and the main objective of this startup was to study aphasia patients. Aphasia means when people have difficulties of speech, of language after stroke. So in particular after stroke. So people with these difficulties of language, this is called aphasia patients. And we studied such people with the purpose to develop electric stimulation of such patients to improve their performance. But I will not talk about patients today. It's another very interesting, very complex story. This is just an example of these experiments, because I will use exactly this data obtained from this experiment. This is why I shortly show that, but I will return to it later. But a very simple idea about that, there is a screen and there is an object shown on the screen, and then the person gives the name of this object, and such session, during one session, usually it's about, for example, 100 of such trials, and all that this EEG is registered during the several stages. So there is image presentation and image recognition and word pronunciation, and inside each of the stages there are many sub-stages and so on, but I will not discuss all of that in detail. And of course also what is very important, so when this EEG data are registered, it's a raw data, and then there are many steps of pre-treatment of this data, which is not at all obvious in particular for me, because I don't know that, and also it requires a very special competence, and there are special people who are trained to do that. So after all that, this data are represented in such a way. So I will shortly explain what is shown here. So horizontal axis is time, and vertical axis, you see there are many curves. Each curve corresponds to one electrode. So if you take, for example, somewhere, well, for example, at the top, it's written here P8. So this is electrode P8. And this electrode produces such a signal, which is shown, this is the intensity of the signal is shown by this curve, and like that for all these electrodes. In these experiments in particular, there are 30 electrodes divided between left and right hemisphere. And then this time, this time shown here, this time corresponds to one trial. It is often called epoch for one trials, meaning for one word. So its image presentation on the screen corresponds to time 0. So here there are 2 seconds, time here measured in milliseconds. So there are 2 seconds before image presentation. So then image recognition, it's from 0 to about another 2 seconds. This is not fixed, it can vary. And then after some small time delay, so there's word pronunciation, which it's shown here, voice onset, voice offset. So this, in fact, this word is pronounced during this time interval, and so on, and like that. This several trials, one after another, registered and then analyzed. Sorry. Yes, and also what is interesting is that, as I mentioned, so there are different frequency bands, and for EEG, usually the frequency range is between 2 and 40 hertz. And these frequencies are, this wide frequency range is divided in several frequencies with more narrow intervals called like delta, alpha, beta. Beta is quite wide. It's sometimes it's divided on beta 1, beta 2, beta 3, and so on. So if, for example, here we take a more narrow frequency band, as is written here, between 6 and 10 hertz, corresponds to this alpha range. So you see these signals, they become more smooth, and here the signals are presented for 5 consecutive electrons, like in a straight line. And what is also interesting here, you see there is this time shift between the signals. So if we follow this maximum of this signal from one electrode to another, it is shifted at time, so it moves. So the signal moves. It's a very interesting question. We call it, not to be silly in the literature, it is called traveling waves, not only in mathematical literature, but also in this neuroscience literature. And this is a very interesting question about existence of such waves, their properties, and so on so far. I will not practically discuss this question today about traveling waves in the EEG data, but it's really a very, very interesting, very important question. And the results which I'm going to present today, it is related. I will not have time to discuss it today. So maybe I will discuss a little bit in more detail some other time. So about this traveling waves in neuroscience, in EEG data, or in other data, because EEG, of course, it's not the only technique how this data can be obtained. So it depends also on the method. But today we will not discuss this question. So what next? We have this, for example, 30 electrodes located at the skull, on the scalp surface, and each of these electrodes produce some signal which changes in time. So from the modeling point of view, we can think like we have these dots, we have some functions of time for each of these dots. It's a signal, and then we can interpolate this function from discrete dots to the whole brain surface. In this case, at each moment of time, we'll have a two-dimensional function of two space variables, as shown here in this figure. The color corresponds to the negative where it is blue, positive where it is red, and all that changes in time. So basically we will use two different presentations. One presentation, we take one single electrode, like here, and we will analyze these curves produced by different electrodes. Space points, because one electrode is one space point. Or another presentation, we consider them as a function of space variable. In this case, it's two-dimensional function. And then we will see also the dynamics, how this function changes its time. So this is what we'll discuss. I will close to finish this short introduction to electroencephalography. And to finish it, I would like to say that, of course, it is widely used both for diagnostic of various diseases and for scientific research, in particular for brain-computer interface. It has a very high time resolution. This is an advantage of this method. And concerning the disadvantages of this method, it has a quite weak spatial resolution because, well, as here we have only 30 these electrodes, because the electrodes are quite big, in fact. And we have only about 30 electrodes. Maximum it can be 20 to 156, but this also has some disadvantage because it becomes, first of all, the equipment itself becomes quite expensive, and it becomes more difficult to interpret this data, even more difficult to interpret this data, and still, even in this case, spatial resolution remains quite low. But what is even more important, if we talk about the difficulties of this method, it is that these results, the results of the EEG data are quite difficult to interpret. Why they are quite difficult to interpret? There are many reasons for that. And one of these reasons, very important one, because that these data are very strongly variable. What this means? And we just were, of course, all that is very well known, but when you deal yourself with such kind of things and you need somehow to understand and to treat this data, so we face this problem that even if we take the same person pronounces the same word, right? The data are different and they can be really very different. So the question is how we can deal with this data if they change from one trial to another one, and how to understand all that. This is kind of a little bit counterintuitive and simple, well, relatively simple chemical, physical, or biological experiments. We used to think that the experiment should be reproducible, right? We consider the same conditions, we do the same experiment, we obtain the same results. This is not exactly the case for EEG data. This is one of the difficulties. But of course, there are many details I will not discuss now. Okay, so now about modeling part. So we have this EEG data. We want to use mathematical model to describe them. So the question is, what model we should take? And this is another very complex question because there are many different models considered in neuroscience, and the most part of them are so-called models of excitable medium. What means excitable medium? The idea is very simple and known for a very long time. So we have a network of neurons, and of course we know that there are many neurons. They estimate about 100 billion in human brain. And there are many connections between neurons. It can be up to 10,000 connections from one neuron to others, to surrounding neurons. So you can imagine these big numbers. I took as example here just this one neuron here, which is connected to these two other neurons, and signals come from this one to this one and from this one to this one. And when this incoming signal exceeds some critical level, so this neuron, which is here, it becomes active. They call it fires. This neuron fires, or in the other words, it produces action potential. And then it produces this action potential. It sends this action potential to other neurons to which it is connected, and like that, all this very complex network can be described as an excitable medium. And of course, there are many models of excitable medium, starting with famous Hodgkin-Huxley model and its simpler version, Fitzhugh-Nagumo model, also Hopfin model, neural mass models, neural field models, and there are many of them. So there is a whole collection of models. And the question is, which of them we should choose if we want to describe EEG data? And my answer today, during a number of years, I was really trying to work with all these models, or some of them, in particular neural field models, from the mathematical point of view or modeling point of view, really very interesting, very nice models, nonlinear dynamics, all these things, just like just a big space for all this mathematical modeling, nice patterns, and so on. So after all these years working on these models, I came to the conclusion that, in fact, none of them. And it was a difficult decision. In fact, it was really not easy for several reasons. So I'm going to talk about today what is called sometimes, well, the terminology can be different, but I think it's a good name for such kind of model, brain source model, and I will explain what this means. It is shown schematically here on this figure. So the circle represents the brain. Well, in fact, we should consider three-dimensional. Okay, it's two-dimensional here. Inside this brain, there are some sources. What means sources? There's some small areas which produce electric oscillations. It is very well known that it is really like that. So brain sources exist. It's not that it is contested. They really exist. They do oscillate. They do respond to external stimulus. And when they produce these oscillations, so it's electric oscillations. So this electric potential, so we know from elementary physics in the middle school that the electric charge produces electric field around it. And as a consequence, this electric field is projected on the brain surface. So let us consider it as a cross-section of the brain. Some sources are inside. This is brain surface. And so this is electric field produced by this electric charge. It is projected on the brain surface. So there are several possibly sources, and all of them project this electric field. And here on the surface, we put our electrodes and we measure here this electric field. So what is the difference compared with these previous models of excitable medium? Because all this part of the brain is inert. It does not produce electric oscillations. It is not excitable medium, as I described before, with these neurons which fire and so on and so forth. So it is inert in the sense that it conducts electricity, but it does not produce any electric oscillations or impulses and things like that. So you see this quite different model, and the question is, first of all, such kind of models also quite often used in the treatment of EEG data, and one of the favorite exercises in neuroscience is when we have EEG data, it's an inverse problem. Having EEG data determine the position of these brain sources, and then it is compared with MRI data and other data, and they say, okay, sources are located there, they correspond to such functional activity, and so on and so forth. We will not discuss at all this inverse problem. We will work with direct problem. We'll suppose that positions of these brain sources are given, and we will determine this electric field on the surface, and we will compare what we obtain with the EEG data. This is what I'm going to discuss today. So, but if we want to choose between these two big classes of models, so we need some arguments. So I will present you shortly some arguments which be used to justify, to explain why this brain source model can be relevant. And in fact, here there are three arguments which two of them I will go on to discuss very shortly, and then this comparing with modeling, this is exactly the topic of my today's presentation. It will be in more detail. So the first question is about potential distributions. This is extremely interesting. I refer here to this paper done almost 90 years ago, work done almost 90 years ago. The first author is Adrian. I think that it is really a brilliant work. I think that it's probably one of the first works where these waves, spatial dynamics of in EEG data was established and discussed. And from this point of view, I think that the progress during the last 90 years, it's not so important. We are not very far from this, from the understanding and from the results obtained in the 1930s. But what is shown here in this figure? On the top, this top curve, so they take a brain from cadaver, from a dead man. They put this electric source called disk here at this point, and they measure this distribution of electric potential around this source of electricity. So at the top, it's dead brain. At the bottom, it's brain from a live subject. So this is dead, this is live, and we see the same distribution. So somewhere we should understand here, of course, they put the source of electricity. Here, of course, they did not do that because there are some sources, these brain sources. At that time, 100 years ago, they called it focuses. So there is some focus of brain source producing electricity here, and there is distribution of electric potential around, and it looks very much the same. So it makes us think that it's really the source of electricity is localized, and this distribution is obtained not because of the excitable medium, not because of neuron firing here, but only due to passive inert conduction of electric potential. So this is the first argument, which seems to me, of course, it's not a rigorous proof. These are some arguments in favor of that. The next argument, but also not rigorous, which can be argued, is that we know that the brain surface has a very complex shape shown here. It contains the solution Giri. So if we suppose that electric signal propagates at the surface as excitable medium, so we can think that in this case the signal should be somehow influenced by this curved surface. So the signal would go like that and like that, propagating along the surface, and then in particular the speed of this propagation would be probably less, or in somehow it should be then noticed in the data. But this is not noticed in the data. So this complex surface, at least in the EEG data, there is no any indication that the signals are somehow influenced by this complex geometry. There is no deceleration, so the speed of signal propagation does not decrease here because of this complex geometry. So again, I repeat that, of course, this is not a proof, because one of the counter arguments that the spatial resolution of EEG data is quite low, and maybe we just don't see because spatial resolution is low. The precise answer on this question is not known. But still, it seems to me that it is also an argument that the signal does not propagate along the surface as excitable medium, as a traveling wave, but it is projected from inside, like a projection, and in this case, the curvature of the surface doesn't play any role because it is projected from inside. And the last type of arguments is, let us just compare what we obtain with different models. So when we used these models of excitable medium, like for example, neural field models, dynamics which we obtained was very different compared with what we observed for EEG data. It's also an argument. We take different models, we obtain results, we compare with experiments, and we say, yes, this model works well, or this model is not appropriate. So let us discuss such kind of arguments. And the first one was, the first experimental data with which we compared such kind of model. And again, it was done again in the same work in 1935. And you see this, for example, three curves here shows this electric potential or difference of electric potential in three consecutive. This is excuse me. This is time. Spatial distribution is here, so this is space, and different curves corresponds to different times. I will not stop on that, but we in some modeling we obtain some very close results to this spatial temporal dynamics. Here it's only 4 consecutive electrodes. So what I'm going to discuss today, it's exactly this question. So how we can compare EEG data with modeling, and I will use this model which I presented now, which is called brain source model, and we will compare and we will see whether the results are appropriate. So first of yes, and what I present now, it's our recent work done this last years. So what is the model? The model is called Poisson equation. In fact, it is obtained from Maxwell equations. But this model now in this form is very simple. It is what is called Poisson equation. So here we have at the left we have Laplace operator, and at the right we have these sources of electricity. And what is also we should understand here, that these sources of electricity depend on time, but the equation itself, it does not depend on time. There is no time derivative. So in this case, t time here becomes a parameter. So for each fixed t, we solve this equation with respect to the space variable. We look for a solution of this equation, and then we change parameter, we change time, so our distribution will change. So we have our domain, we have our equation. F corresponds to brain sources, I will explain a little later. And also we have these boundary conditions, which in mathematics called Neumann boundary conditions. It's a standard formulation for such kind of problems. So what about sources? We suppose that our sources are very small. Mathematically speaking, these are delta functions. For example, here it is written for two sources, two delta functions located at two different points. The first one is x1, the second one x2. And since these sources are oscillating, we multiply them by some oscillating function, time oscillating function, and the simplest one is a sinus with some frequency and some phase. I will return to this question of frequency and phases. But before that, another important question is, if we consider such model, so we need to ask the question whether there is a solution of such problem. And here we are exactly in the mathematical problem. I will pronounce some with enormous pleasure. I will pronounce some mathematical words. So this is what is called elliptic problem in a bounded domain, and what are solvability conditions of such, by the way, it's a linear, it's the simplest, it's a linear elliptic problem, just Laplace operator, Poisson equation. So the question is whether we can solve it or not. And the answer is, of course, very well known, because this question is studied already during about 250 years, beginning from the work of Gauss and then Laplace. By the way, this equation, no, not this equation. Such kind of equation with F equals 0 was written by Laplace. And he used this equation to describe exactly the distribution of electric potential. But he did a mistake, because he didn't take into account in this equation exactly these electric sources. So his pupil Poisson later, don't remember, about 20 years later, corrected this equation. He introduced this F, distribution of electric charge, and since that it is called Poisson equation. But it is studied for many years, and the theory of elliptic problems is very, very well developed, especially during the last 100 years, in particular in relation with the works by Frick-Wall, who introduced Freedom operators, Freedom alternative, and then it was developed for wide classes of elliptic operators. So we know the solvability conditions for such kind of equation, and the solvability condition is written here. So the integral of this function f should be 0. And this is very important for these applications. People using EEG use this condition even without knowing all this mathematics. For example, when they do electric stimulation of the brain with electrodes, so this condition is necessarily satisfied. But okay. So what this means for us? Let us consider the case of two sources, this one and this one. So the integral of f, space integral of f, should be 0. So if we integrate with respect to space, so this delta function disappears. We have only this sinus, and this delta function disappears. We have this other sinus. So the sum of these sinuses should be 0 at each moment of time, because this condition should be satisfied for at each moment of time. So this, for example, if we take here different frequencies, so they cannot, this condition cannot be satisfied. So the frequencies should be the same, and the phase should be opposite. So then it is the same sinus with the opposite sign. So this is with plus, this is with minus. Their sum gives 0, and this solvability condition is satisfied. I should accelerate a little bit, otherwise the most interesting, I will not have time for that. So, now we have the problem. We have equation, boundary conditions, the form of this f, and we will begin with the approximate analytical solution. And this approximate analytical solution can be constructed with Green's functions. And what is Green's function? So if instead of this bounded domain which corresponds to the brain, we consider an infinite space, so this Green's function has a very simple form. So this is an approximation. We say that we have this big head, small sources are inside, sufficiently far from the boundary, so we can approximate this Green's function in the bounded domain by this Green's function in the whole space. In this case, it has a very simple form, and we have a very simple analytical solution. Moreover, exactly the same simple analysis can be done not only for two sources, but for any number of sources under some conditions. So look at here, look at this formulas here. So we have f, which is written like that, but instead of sinus with phase p here, we just write it as sinus with sign minus here without p, and then we can write this like that. We have some function of space multiplied by this, the same sinus from this term. Anastasia, I see only you, so only you can confirm me that you understand and you agree with what is written here. Is it clear? So that in this case, if now even if we take many sources and many many terms like that, if we have the same sinus everywhere, so we can write it in this form, some function of x multiplied by the same sinus. In this case, we can easily solve this equation. So if this function f is written here, so we solve this equation without sinus, just delta u equals f0. We find the solution u0, and then we multiply the solution by sinus, and this will be exactly the solution of our equation for if f has such form, because it is a linear equation, and the same sinus enters the right-hand side and the solution. Well, hopefully this is clear, because this is very simple. Okay, now we have our solution, which is like that. It is some function of space multiplied by this periodic function of time. So how the solution looks? I try to explain it here. If we consider, first of all, this solution as a function of space variable. So we have this function u0 of x shown here. And then we multiply this function by this periodic function of time, sinus kt, and this solution begins to oscillate. You see, we multiply it everywhere by the same function, so at some time later, it becomes like green curve here, so it becomes positive here, but negative here, and all the time it oscillates like that periodically in time. If we consider this now, this solution as a function of time, so we have, for example, if we take this point here and we measure it, it's a periodic function of time shown here. If we take another point, it's another periodic function of time here. So, and like that, we can measure the signals in all space points, which corresponds to all these electrodes. And now what I show you here, it's this solution, this analytical solution for, I don't remember, probably 4 electrodes or something like that, or 3 or 4, yes, 4 electrons. Yes. So what is important here? Because our solution is written like that, some function of space multiplied by this periodic function of time. So all these electrodes will give these curves like that, which are synchronized in time. You see that all these functions become 0 at the same moments of time. At what moments of time? Exactly at moments of time when sinus equals 0. We multiply by 0, so all our signals equal 0. So we have this representation like that, and this is what is called standing waves. And if we consider the standing waves like these are already numerical simulations for this three-dimensional spherical domain. So the standing waves, and in this case there are three sources. So what we have here, so for some moment of time shown here at the left, we have these two sources here with this blue means negative, red means positive, and sometime later it is exactly the same but in reverse. Blue becomes red, and vice versa. So, and like that, this function oscillates in time, but it does not change in space. It's exactly the same spatial function, but multiplied by this periodic function of time. For example, if we take this line here where the solution vanishes, where the solution equals 0, so this line does not change in time. So these oscillations happen like that periodically in time, but the spatial distribution does not change. This is important, and this is what is called standing waves. Now, if we take, I finish with two sources. If we take now 3 sources, as written here, the situation can be the same. If we take the same frequencies and phases, it will be exactly the same. We'll obtain standing wave. If we have only 2 sources, then there are no other possibilities because of the solvability conditions. But if we take 3 sources, the situation can be different. Look here. Here we have, I write now f in such a form that there's the first term here with 1 frequency and 1 phase, another term with another frequency and another phase, but the third term, I take the same, but with the sign minus. Yes, with the sign minus. You see here this minus. So when we integrate this with respect to time, these delta functions disappear, and we have a1 sinus k1, a2 sinus k2 minus a1 sinus k1 minus a2 sinus k2. The solvability condition is satisfied. So we will have the solvability conditions for any arbitrary values of k1, k2, phi1, and phi2. So frequencies and phases can be different if we consider 3 sources or more. It cannot be like that for 2 sources, but for 3 and more, it is possible. And this is very important. This is exactly what I'm going to explain now. So, so this left, it's again, I come back to approximate analytical solution for 3 different cases. The left case, what we discussed before, the same frequencies, the same phases, we have standing waves, and these oscillations are perfectly coordinated. They vanish at the same moments of time. If we take now the same frequencies but different phases, there are phase difference in sources. You see, there are also phase difference in solutions. They don't vanish at the same time. They vanish at different moments of time. So there is a phase shift. Behavior of these electrodes are not so well coordinated as before. And the third case, if we now take different frequencies, here it was different phases. If we now take different frequencies, it's another property which appears that the amplitude of this oscillation is not constant anymore. Here you see phase is different, but the amplitude are the same. But here the amplitude also depends on time. This become modulated oscillations. So these are three different cases, and you'll see below. That something like that happens also in the data. And now let us, so it was, previous slide was approximate analytical solution, and now direct numerical simulations of three-dimensional problem with these three sources with different phases. So the first moment of time, the distribution is like that at the left. So a little bit later, you see what happens. This blue area doesn't move. This red area at the top doesn't move, but becomes a little bit larger. So the source like increases, but this one gradually disappears. And after some time later again, this source, well, not the source, sometimes we call it peak or hotspot, but whatever it is, it completely disappears. It moves here. And at the same time, this blue area moves from here, it moves here. And this is not a complete period. I just showed here in detail this dynamics that this solution begins to rotate. And yes, okay. Now I make a short break and I introduce, in the results, and I introduce a software which is called SimNIPS. And here the interest of the software is that they consider realistic brain geometry shown here, and not brain sources, but stimulating electrodes, but still it is possible to do something similar. So I really don't have too much time to discuss it in detail. I had a video here, but something happens, it doesn't work. As usual, not important. We move further. Yeah, it works. Well, it's the simulations, how this, you see, like it turns this around. Yes, and here it is the same result with the same software, but this electric potential is projected on the circle. So here it was complex geometry for complex brain geometry, exactly the same result we projected on the circle to compare. Again, I don't see whether it works or not. Okay. So look, you see, like this, if you follow this red dots, red like areas, it moves like that, more or less around during some time, and then, okay, I will anyway. So it turns around during some time, and then it changes the direction of rotation. So it depends. If you take different phases but the same frequencies, it turns all the time in the same direction. If the frequencies are different, it turns one way and then it turns opposite way. If we take this software and we consider just electrodes, as I discussed before, we have the same three cases as shown here. When the phases are the same, you have the synchronized oscillations. When the phases are different, you have this phase shift. And when the frequencies are different, we have this amplitude changing. All that was just theoretical studies. We are not yet at the data, but my time is almost finished. Anastasia, my time is finished. I don't know what to do. I was very slow in my presentation. Can I have at least 10 minutes more? Whether our audience give me 10 minutes more, because the most interested is just in front of us. What do you think, Anastasia?
I think we're all very interested, and you have 10 minutes more.
Okay, so thank you. So this again, these are the results of this projected on the circle of numerical simulations. What we see here, I will discuss it in more detail later to gain some time. These are consecutive moments of time, the upper row, the lower row, this red area moves like that. I will explain this motion a little bit later. Now we come to the EEG data obtained in this startup course team. Unfortunately, course team has finished its work, but this startup does not exist anymore, but I will present some results obtained here. So these are these picture naming experiments, image, word pronunciation. This is how this data looks, we discussed. So we take now this data, and it appears that it can be quite different. First of all, we need to understand that since there is such a high variability in the EEG data, what they usually do, they consider averaged data. Averaged. So if we have 100 trials, meaning 100 words, let us take for each of these words, we do exactly this work. We take all these electrodes, all the signals, we take an average signal with respect to all these 100 trials. This is called ERP, event-related potential. Never mind. So what we have here, and here I show you this average data for 100 trials. And we see here exactly these standing waves. The amplitude changes. Why the amplitude changes? Because it corresponds to different brain activity, to image presentation, image recognition, to word pronunciation, and so on. Here, this first 400 milliseconds, it's image recognition. So we see here this exactly standing waves where all these electrodes vanish at the same time. If we look at these maps shown here, sometimes they're called topographic maps, whatever. So we have exactly standing waves. We see exactly, if we look at this red area here, it is practically exactly the same as red area here. And in between, it is inversed. What was red became blue here, and blue become red, and so on. And this repeats in more or less exactly periodic way. So this is what we call standing wave, and this corresponds to these numerical simulations or analytical results shown here. This the first regime, standing wave. We find it in theory. We find it in the data. The next regime, if phases are different. So you see now these electrodes are not so well synchronized as before. There is a phase shift. And if we compare with theory, it corresponds to our modeling with three sources and phase and different phases. And also, if we consider now these topographic maps, they are not exactly the same. They move because of this phase difference. And finally, if now we take the third case, you see these modulated oscillations, and we have exactly the same modulated oscillations if we have different frequencies. So this is what we have for average data, right? Now, what of course is also very interesting is individual trials. So not average data, but each trial taken individually. And this is a movie from EEG data corresponding to one trial, meaning to one epoch or one word. Like, you see how it moves. So it rotates this way. You see it rotates like up. No, not now. Okay, now it changes. You see it goes through the center and splits, goes back here. Then it changes the direction of rotation. Again, it goes through the center and splits and go up. You see, it's another regime, and so on, so far. I stop on that. Okay. So if I take from this video I showed you, I take it's only one trial. It continues 3 seconds, but there's a very high time resolution. There are hundreds, even maybe thousands of these frames. So I take several of them corresponding to one period of these oscillations, and how it happens. We see this red red area. It moves like that, it rotates, it makes one period, it returns back exactly to the same position. So it's one period of this rotation, we call it rotating regime. So now I want to compare what we have in the data and in the simulation with three sources, and to emphasize some properties of these regimes. What are the properties? So look, let us analyze these regimes. Let us spend, 3 minutes more. I suppose that if some of from the audience, if you are busy or if you are bored, so no problem, you can of course leave. But I would like to explain what is happening here because I think that this is interesting. So let us look at this red area here. And I call this, it rotates counterclockwise. Because of that, I call this edge, this part, forward front, and this part backward front. So when we go from here to here, the backward front does not move. It is exactly as it was, but this forward front, it goes like that, and because of that, this red area becomes larger. If we take the next one, now the forward front doesn't move, but now the backward front from here move here, like here. And so, and it continues exactly in the same way. So this rotating regime is not uniform. It's all the time it is an alternation of motion of forward front and backward front, one after another. It is shown here. If we take now these modeling results, we have exactly the same behavior. So again, this red area, we see the backward front doesn't change, the forward front moves, rotates, then it does not move, and this backward front moves, and so on. So we have the same alternating motion of this, like I call them hot spots, these red areas, the same as blue areas. This is the first property. The second property, we have two different situations. Either the direction of rotation does not change, for example, counterclockwise, or it can be first one way and then it changes to the opposite way in the data. And the same we have in simulations. If we have the same phases, if we have the same frequency but different phases, it rotates all the time one way. But if we have different frequencies, first it rotates one way, but then it changes to the opposite. So this is the second property. The third property is, of course, I should mention, I wrote here that these are periodic regimes, meaning that, you see, it's, well, in fact, when we observe the movie, it is possible to do it even more precisely. That's the last one, because it's not the last, because it's one period of rotation, but the next frame here would be exactly like this one. This is not exactly like that, but the next one is exactly like that. I didn't show it here. So this regime is exactly periodic, and its periodicity can continue, well, several times, 5, 6, something like that. Then it can change to some other regime. And what is also interesting here is that if you compare this, the upper row and the lower row, they're exactly the same up to change of the color. Red here becomes blue, red, blue. So it's again very well coordinated during one period. It changes sign, and it is exactly the same in the simulation if you compare up and lower row. So it's up to opposite side. So we see this comparison shows that these modeling results are very close. I would say not only quantitatively, but not only qualitatively, but even quantitatively. in this properties, but also just the images itself are very close, look very similar. So what next? The last one, I will not take too much of your time more. So I want just to show another regime which we often observe in the data, and we call it symmetric regime. And when I showed you the video with the data, I brought your attention to such kind of regime. So look what happens here. So we have this red area here. It splits, it becomes larger. It splits into two red areas like that. They move up, like here. They move at the top. And it continues, well, still, because again, as before, there is this alternating motion of forward and backward fronts. It's also the same here. This is why this backward front continues this motion up, and when this red area concentrates at the top, it goes down along the center of this, along the central line, and it returns back here. And again, it is a periodic regime, but the motion is different. And again, we can model such kind of regimes with, now not with 3 sources, but with four sources. We cannot model that with 3 sources, but we can model that with 4 sources. It is shown here. At the left, it's exactly the same as in the previous slide. In the right, these are modeling. The presentation is a little bit different, but we can see that the behavior is the same. So this red area is at the bottom. It moves up both ways. Then we have this concentrated, like here. I'll compare this one in the data with this one in modeling. Then it moves up to the top. We can compare this image with, for example, this one, and then it goes down through the center, returns back to its initial position. So again, this symmetric regime, which we observe very often, probably in the individual data, probably this symmetric regime is what is observed most frequently. So we can obtain something very close in modeling with 4 sources. So conclusions. So we observe this standing waves. By the way, what is also interesting, that standing waves are often observed in average data, but they are very rare in individual data. In individual data, we often observe this rotating regimes and symmetric regimes. We can reproduce them in simulations, and comparison is quite good. There are some other more complex dynamics we did not study yet. I don't really know. It's really more complex. I think that it's a very interesting question, but at the moment we don't know the answer, how to model this more complex dynamics. And conclusion of all that, it seems that the model, this brain source model, is appropriate to model EEG data. The results are quite similar, and I return back to the beginning of my discussion that if we take the models of excitable media, we do not obtain such regimes. And one additional question for further discussions, there are many of them, and one of them I keep for maybe for the next time, I don't know, about these traveling waves, because traveling waves can be modeled in excitable medium. Here, with all these regimes, these are not, well, mathematically speaking, these are not traveling waves. This is something different. To make a difference between them, maybe call them moving waves. And in fact, these moving waves, it comes back to this old work on 1935. They call them also moving waves. It's not the same. There is a difference between them. And a very interesting question is about these waves, because there is a big literature in neuroscience about traveling waves in different kind of data, not only EEG data, but other data like MECOG data and other data, whether they observe traveling waves. So the result, of course, can depend on the spatial resolution and so on. But my actual understanding for now is that in the EEG data, these are not traveling waves, because to have traveling waves, we need this excitable media, but these are other regimes obtained with this brain source model. I stop on that. Sorry for being a little bit late. Thank you for your attention.
Thank you very much.
Okay, so I don't know if there are questions, Anastasia. You are supposed to ask about the questions, or I do it myself. So if there are questions, we can. Yes, I see some hand raised. Please, I don't.
You should move up this.
Yes, yes. Елизавета Алмазова, please.
Hello?
Yes.
I wanted to ask, so in the model we have used delta functions.
Yes.
But I didn't quite got the point of using them. Maybe there is some kind of biological sense in it.
Well, you know, for approximate analytical solution, it is very useful, very convenient, because we can use this analytical solution based on the Green's function. In numerical simulations, in fact, well, I did not show the details of the simulations, but well, it is done for, well, not a, it is done both for delta functions. Well, of course, taking into account that in numerical simulations it cannot be exactly delta function, it is approximated delta function, but it is also done for small sources, not exactly for point-wide sources, but small, but not point-wide, with some dimension. So so delta function is a good approximation. In numerical simulations, we can consider not necessarily delta functions, but some small sources with a finite size. In reality, I mean, in our brain, well, the size of the sources, of course, it's not exactly known. I would estimate it as several millimeters, probably, and this is quite small in the scale of the brain. So in some sense, it can be approximated also by delta function. But what I should also say is that these numerical simulations, which I showed you with this software, if you remember, I showed you this software called SimNIPS. In fact, this modeling is done not at all with delta function, but they are done with electrodes with STIP. In fact, this is software developed to model stimulating electrodes, and the stimulating electrodes, they are quite large. And their form can be also different. It can be circles or it can be squares, but they are really quite large. It can be, I don't know, 1 centimeter, 2 centimeter, like that. But the results are quite similar. The results are very close. So I think that, in fact, in some reasonable limits, the form and the size of these sources are not very important.
All right, thank you.
Well, if there are no...
I have one small question. Could you please comment, when you show the experimental data, these two regimes, rotating and symmetrical regime, were obtained in one experiment, as I understand. And in your model, you obtain it with different source functions. So this is two different models where you obtain rotate regime and where you can obtain symmetric regime. Could you please comment this? Yes. Whether can we obtain both regimes in one model? Maybe if we consider more sources.
Well, the point is that we have one single head, head in French, head. So how the same head can produce different regimes? This is your question. In other words,
can we model this one head with one model, not with different models?
No, but why? How our? But what I'm trying to say.
Yes, maybe.
What I'm trying to say is that the same head produces different regimes. How it happens? Because, in fact, inside our head, there are many brain sources. Not 3, not 4, but I don't know how many, but many of them. So my understanding is that different sources or different number of sources are activated at different moments of time. So think that you have 100 sources in your head. You have some external stimulus coming, like visual stimulus. You look at the screen, and this visual stimulus activates some sources. For example, it can be 3 sources. If it is 3 sources, so we have this rotating regime. But like, for example, 100 milliseconds later, for some reason, another source is activated. We have 4 sources, and the regime can stay the same, but it can also change.
Mm-hmm.
And since there are so many sources, and since we have so many activities at the same time, where this variability comes from? In particular, because we do many things at the same time. We use our eyes, our ears, other senses. We have all this complex physiological activity, which is also governed by the brain. We move our hands, for example, or even our eyes. This is very important because rather often we don't control eye motion, but it can influence the EEG data. So there are special electrodes put here which control eye motion, and this is somehow taken into account in the data treatment. So you ask whether we can describe different regimes with the same model. Yeah, why not? We can take 4, for example, we can take 4 sources. If one of them is inactivated, we have then 3 activated sources with rotating regime. Sometime later, this 4th source is activated. We have the symmetric regime. But of course, I did not show. There are many details which I did not discuss today. We observe symmetric regimes. So what I showed is symmetric regime. It's like motion like that, like a vortex, like that, and goes down vertically like that. But rather often, it does not go vertical, but it is inclined like that. So the direction can change. You see the direction of this.
Yes.
So it is the same. It is the same symmetric regime, but it is turned a little bit. So how to obtain that? Also with 4 sources, but the location of these 4 sources should be different. I cannot give more precise answer because this is very complex. It is of course known that there are many different sources. When they solve this inverse problem, what I mentioned in the beginning, they have EEG data. Let us determine the sources from the EEG data. And they do it, but they find like that many different sources. Not 3, not 4, but much more. So this inverse problem gives many sources, and it is very difficult. Moreover, the solution of this inverse problem is not unique, and it is very difficult to understand what is happening. This is why the solution of the direct problem, not of the inverse problem, but the solution of the direct problem, when we know that 3 sources give such behavior, or 4 sources give such behavior, I think that this helps us to understand all this dynamics.
Thank you.
Well, if no other questions, then I thank all listeners again, and have a good day. Goodbye.
Thank you very much. Goodbye.
Goodbye.
Thank you.